time so far this semester talking about how we get energy from glucose. Now we're going to talk about how we get energy from fat. Lipid metabolism. So we're going to talk about how when we eat fat, what do? We have to first hydrolyze the triglycerides, get that glycerol off, and make our fatty acids. Then what we have to do, because beta oxidation happens in the matrix, we have to get it into the matrix. And it's not simple. In fact, I think it's silliness. It's kind of weird what the cell does to get that fatty acid into the matrix where beta oxidation happens. So we're going to talk about getting it past the two membranes, strangeness. And then we're going to talk about beta oxidation, which is super cool. It's very simple. We're going to compare, and we've talked about this before, how we get more energy, carbon for carbon, out of fats than we do out of glucose. And then we're going to talk about the oddballs, odd number of fatty acids, what do we do with those, and unsaturated fatty acids, how do we handle that? Then we're going to talk about another class of molecules, ketone bodies, where they result from. And it's really from having too much acetyl-CoA. And then we're going to talk about oxidative stress. So let's talk about fats. Fats are the primary storage form of energy. All right? Why would they be the primary storage form of energy? What do you think? I already said it. You know, but why do you think you can get more energy from a fat than you can from a carbohydrate? Think about the structures. Look at the carbons on your fatty acids compared to the carbons on your glucose. There's more. It's not, but carbon for carbon. If you compare the one carbon from, or the same number of carbons from a fat, it doesn't matter. So what is the process of getting energy? What are we doing? We're burning, right? We're going to carbon dioxide, right? And we said that metabolism, instead of burning, we're slowly burning. You're slowly oxidizing each carbon to carbon dioxide. So, so the process is still the same. So what we have is like a ladder. The top of the ladder is carbon dioxide. And each step up, instead of lighting it on fire to burn the glucose or fatty acid to get the energy, the product is the same, carbon dioxide and water. But what we're doing is we're doing a slow burn. And each time you go up a rung of the ladder, you're capturing energy. When you start out with a fatty acid, most of the carbons, except for one, are all carbon-hydrogen bonds. When you start out with a carbon on a glucose molecule, it's carbon-oxygen already. Carbon dioxide is carbon with two oxygens. So here's our ladder. All right. The top of our ladder is the ultimately oxidized. So this is a C double bond O. Let me write that here. C double bond O. So here we are at the top. C double bond O. When we have just carbon, hydrogen, another carbon, we're basically at the bottom. When we have our carbohydrate, we're already partway there. So we're going from carbon, no oxygen bonds, to carbon, two oxygen bonds in metabolism. That is the process. But when you start out, so here's a fat, and this is a carbohydrate. When you start out with a carbohydrate, you're halfway there already. Maybe not that much. I put it at half the middle. I would say it's maybe one rung up, But you're already there because we've got to get to the double bond there. So we're starting up higher in the ladder. We have fewer steps to get to that C double bond O, to the carbon dioxide. Here with the fat, you have more steps to go through to get to the carbon dioxide. So each step each time we go up the process of getting to carbon dioxide, you're going to get energy out each time. So the more steps you have to get to carbon dioxide, the more energy you're going to get out. Because we're already up on that ladder with carbon dioxide, with carbohydrates, we are going to get less energy out.
Can you say that last part one more time?
So every time you go up a step of the ladder to get to carbon dioxide, you're releasing energy. We're starting at the bottom. We have a reduced carbon. This is reduced carbon. This is oxidation, to go oxidation or burning. All right? So to get the energy out is an oxidative process. And what we're doing, if we just burn it, we're going from the carbon reduced form to the ultimately oxidized carbon dioxide. So here, what we've done is we've already had a little bit of oxidation go on with our carbohydrate. So there's fewer steps to get through in order to get to that carbon dioxide. Because in order to get from carbon-hydrogen bonds to carbon to oxygen double bonds, you're starting at an earlier starting point. Here, you've already got a carbon-oxygen bond. So you've got a head start. But you're not going to gain as much or give up as much energy because of that head start. So think every time you climb a rung of that ladder, you're releasing energy to get to your carbon dioxide. So I said the carbons in the chain of our fats are highly reduced. Remember, carbon-hydrogen bonds are a reduced form of carbon. Carbon-oxygen bonds are the oxidized form of carbon. Carbon dioxide is the ultimately oxidized carbon. That's why it's the production of burning. Burning is the same thing as oxidation. When you burn, you react with oxygen. So this is an unfair comparison, but we'll do another comparison later. So glucose only gives you negative 15.9 kilojoules gives off, so that's why it's negative. And palmitotic acid, which has 16 carbons, gives you off 38.9. So, but we're going to compare it later, all right? We're going to do a better comparison later because it's not the same number of carbons here. But we'll see later that we get more energy, not much more, but more energy out of our fats. Okay, so what do we say the first thing? You eat your steak and you get a triglyceride. That sounds good. Eat your steak, get your triglyceride, but what we're going to do is we need a fatty acid out of that. So what do we have to do? We have to cleave the ester bonds from the glycerol. So what we're going to do, remember I said esters are little old weak ladies. They're very susceptible to hydrolysis. So we use lipases to get, and water, to get our glycerol and our fatty acid. We can either reuse it to make membranes or whatever we need to do, or we can go into beta oxidation. Now, if you have a phospholipid here, or a phosphatidylcholine, whatever you have, if it's got a phosphate, we're going to use a different enzyme. So you need different enzymes, actually, to break apart different parts of our triglyceride. Here we have a phospholipid, and we can see like the N1 would need one enzyme. Here the middle guy would need a different enzyme. So there's a lot more going on than what I'm telling you. That's all you need to know from this slide. There's a lot more going on. All right, so we have to get our fatty acid. So we've eaten our steak, gotten our triglyceride. Our enzymes in our intestines have broken it up, and now we have to get it into the matrix where beta oxidation is happening. How do we do it? We cannot get a fatty acid through the membrane. So what do we have to do? Well, remember, just like with glycolysis, you have to put in energy to get energy out. This is the same thing. What we have to do is put in energy. Actually, we're going to count this as 2 ATPs. because we're giving off 2 phosphates. We're going from an ATP to an AMP. So we're going to count this as 2. I know, it's kind of weird. We're going from an ATP to an AMP. And so mono, adenosine monophosphate. Adenosine tri to mono, 3 to 1. And this PPI stands for 2 phosphates, 2 inorganic phosphates together. All right, so you put in that energy, you get your fatty acid with your AMP, and then you react it with a coenzyme A. Remember, the sulfur part of the coenzyme A is the one that does the work. The AMP, what it does to the fatty acid is it polarizes this carbon so that it will be more partially positive, so the sulfur can nucleophilically attack it. So then you get acyl-CoA. Acyl, an acyl group is the carbonyl with a carbon chain on it. An acetyl group is it's just 1 carbon. So an acyl group, this is an acetyl group. So C double bond O/R, meaning like long chain. I'm sorry, you can't see it. Long chain, that's an acyl group. C double bond O connected just to 1 carbon, that's an acetyl group. So this is an acyl-CoA. And we need to put in energy to get the coenzyme A on. So here, this is the overall reaction. This is a thioester bond, and this takes place in the cytosol. These fatty acids, if they are stored as triglycerides in your fat tissue, it will be released in response to a hormone binding to the surface of the cell. Okay, so here, that gets you through the outer mitochondrial membrane. The coenzyme A will get us to the outer mitochondrial membrane. Beta oxidation happens in the matrix. So now we're in the inner membrane space. The acetyl-CoA, or the acyl-CoA cannot get through to the matrix. It cannot get through the inner membrane. The outer and inner membrane of the mitochondria are different. So the outer membrane is permeable to the acyl-CoA. The inner membrane is not. Why, I don't know, but it's not. What we have to do is we give it to, that acyl group is given to carnitine. Carnitine then can carry it through the inner membrane. So we take in the inner membrane space, we have carnitine. Here I'm just showing you 2 different structures. This is carnitine, and this is also carnitine. Okay? I'm just showing you the structure in a different way because it's sort of hard. Carnitine is both positively and negatively charged, so I think that's what helps it get through. So you give it up from the coenzyme A, you give it to carnitine, now it can go through to the matrix, crosses the inner. All right, so this is where we're at. Let's take a look at this picture. Here's the outer membrane, right here, and here's the inner membrane. So what we have is our fatty acid, and it gets put together with our coenzyme A in the cytosol, and now we have our acyl-CoA. It can get into the inner membrane space. This cannot get through here, this inner membrane. So what we have to do is it's going to be reacted with carnitine. The coenzyme A gets released and go back to be reused. This acyl-carnitine, so acyl group from the fatty acid, carnitine over here, it's going to help it get through the inner membrane. But what are we going to do next? This is why I think it's kind of weird. We're going to give it back to coenzyme A. It was just with coenzyme A. Why do we do that? Why do you think we're going to do that? We have to give it to something that can't get through the inner membrane. What if the membranes were permeable to coenzyme A? It would just go back to the cytosol, right? That's why you do it. So it's kind of weird. I think, until you think about it long and hard, why do we give it to coenzyme A, then give it to carnitine, and then give it back to coenzyme A? Because if both membranes were permeable to coenzyme A, then we wouldn't have beta oxidation happening. It would just go back, right? It would just go back into the cytosol. So we need that carnitine in order to get it through the inner membrane. And now we're ready for beta oxidation. We're at the point where we have the acyl group activated with the coenzyme A in the matrix. This is where beta oxidation is happening. So you guys need to know what is needed to get out across the outer membrane and what's needed to get across the inner membrane, and why would this whole thing happen? Why can't you make it permeable to coenzyme A? Because then your acyl group would not be available for beta oxidation. So let's start discussing beta oxidation. This is only 4 reactions. It's just so lovely. You don't need to remember 8 or 10. This is only 4. And again, they're all enzyme catalyzed. And what they do is the whole purpose of beta oxidation is to chop our long chain fatty acid that's been activated with coenzyme A. It's to chop it into acetyl groups. So what we're going to do is we're going to chop between the alpha and beta carbon each time. So what we're going to be doing in beta oxidation is oxidizing the beta carbon. That's the whole purpose. In beta oxidation, we're going to be oxidizing the beta carbon. So we number, and if you've taken organic chemistry or even the last part of Gen Chem 2, you study organic chemistry. And you learn that an acid carbon is always numbered the first carbon. So this is carbon 1, 2, 3. So sometimes we don't want to use, it wouldn't be very pretty if we said third carbon oxidation. So we use Greek letters. Alpha is the one next to the carbon number 1. Beta is 2 away. So it's going to be third carbon oxidation or beta oxidation. So let's look at the 4 steps. How are we going to chop right here and make this activated with coenzyme A so it can happen again? Sometimes they call it a beta oxidation spiral because it keeps going until we're all done chopping up our fatty acid. So what we're doing first is we're going to put a double bond between the alpha and beta carbon. We're using FAD because that is the stronger oxidizing agent that is going to be able to put a double bond there. Is this some money? How many ATP can we get? 1.5. You guys know your stuff. All right. So we're going to oxidize that. Putting a double bond in is oxidation. Not just putting in a carbon-oxygen bond. Putting in a double bond, you're removing hydrogen. So that's an oxidation. Something else has to be reduced, and we get our money molecule. It's not a lot of money, but it's some. So that's where we're putting that in. Reaction 2. Oh, I can see what's going to happen. We're hydrating, right? And we're adding to a double bond. You put part of the water molecule on one carbon and the other part of the water molecule on the other carbon. So H2O, you have an OH and an H, right? And H2O. So the H is going to go on the alpha carbon and the OH is going to go on the beta carbon. Hydrate that double bond and put that OH. What do you think is going to happen next? You guys know. What's going to happen next? You have an OH here. Beta oxidation. Beta carbon. We're going to oxidize this OH to what? Yeah, to a carbonyl. So here we're going. Now we know that the oxidizing agent to put in a carbonyl to oxidize an alcohol is NAD. We're going to oxidize that to that. And so we get money. How many ATPs can we make from NADH? 2.5. So that's going to go on to the electron transport chain. So far, we've got 1.5 from the FAD, 2.5 from the NADH, right? Just by doing this oxidation. Then what do you think it's going to do next? Cleave it. Now, you guys knew this before it even happened. You could have gotten up here and taught this, right? So we're going to cleave that by taking another coenzyme A, and that coenzyme A, sulfur, is going to do a nucleophilic attack of the new carbonyl. That's going to push this or break this bond, and so now we have an acetyl-CoA. Where do you think that acetyl-CoA is going to go? It's already in the matrix. What pathway has an entry molecule of acetyl-CoA? Citric acid. So this is going to go on to citric acid and get our 3 NADHs and our 1 FADH2 and our 1 GTP, which is equivalent to ATP. Right?
Sorry, can you say that?
No, I'm just saying what I got out of.
No, but the beginning, what the sulfur.
The sulfur here.
Yeah.
All right, so you want me to repeat this?
Yeah.
The sulfur here, sulfurs, like it did before when we were doing our activation, sulfurs like to attack the carbonyl. Well, this one's already got sulfur on it. So this new coenzyme A is going to attack the carbon of a carbonyl. And that cleaving, or that attacking will cleave this bond because carbon only can have how many bonds? 4 bonds. So if the sulfur formed a bond here, then that would be 5 bonds, and that carbon would not be happy. So we're going to break this one because this will make a better leaving group for you organic chemists. And so here we get an acetyl-CoA that will go off. You can do like a little arrow. Citric acid cycle. Yes, Emmanuel. Sure. Want to go back to the last slide? Okay. All right. So this is going to go off the citric acid cycle, and now we have a new acyl-CoA. How is this different from our starting material from beta oxidation? It looks to me the same. It's got this red R, C double bond O. How is it different? It's going to be shorter by how many carbons? 2, right? Because we just got rid of these 2. This is the old beta carbon. So this new one, this product, is 2 carbons shorter than the starting acyl-CoA. What do you think we're going to do with this? So this is going off to the citric acid cycle. What are we doing with this? You're going to keep going. So we're cleaving that with that, and we're going to go, well, look at this. So you can imagine it keeps going until we have 4 carbons left, and then we do 1 cleavage. So let's look at this again. You have your fatty acid, and it's activated with our coenzyme A. We're going to put a double bond. You don't need to know any of these enzymes. We're not going to talk about control here. So we're going to put a double bond here. I need you to know that you're using an FAD for this. And we get some cash here, 1.5 ATPs. Then once we have that double bond, we're going to hydrate it. Remember? Malate or malate to fumarate to oxaloacetate. Or did I have that backwards? Yeah, all right. Malate has the OH, so okay. So then succinate to fumarate to malate. I'm sorry, it's been. All right, I have it backwards. Don't take points off. All right. So, but look at what's happening here. It's the same thing, right? It's the same kind of idea where you want to have oxidation happen. How are we going to do that? You got to get a double bond in there that you can hydrate and then you can oxidize. Right? Same idea that we're having here. Double bond, hydrate it, oxidize that new alcohol, and then this is the new one. We're going to cleave it using another coenzyme A. So this is really the only new kind of reaction that we haven't seen before, where we're putting in a sulfur to attack the new carbonyl, and then that will cleave it. And then we have a fatty acid that's 2 carbons shorter, and there we go. So each cycle is going to give us an FADH2, an NADH, an acetyl-CoA, and right here, acetyl-CoA, and a fatty acid that's 2 carbons shorter. Yes, Emily?
You said that it keeps going through until 4 carbons are left, and then does it cleave again?
Yeah.
So it finishes when there's only...
Yeah, we're going to talk about that. So it keeps going until there's 4 carbons, and then we'll cleave there, but the last one gives you 2 acetyl-CoAs, so it doesn't keep going.
Can you repeat the products?
So the products of beta oxidation for each cycle, each spiral, is going to be an FADH2, an NADH, an acetyl-CoA, and a fatty acid 2 carbons shorter. Let's talk about how many times it's going to happen. So let's say we start out with 18 carbon fatty acid, sterile CoA, activated with coenzyme A. Let's first talk about how many acetyl-CoAs are you going to end up with? What's this number here? 9. Okay, because if you have 18 carbons, you're going to get your 2 carbon acetyl-CoAs. So 18 divided by 2 is 9, right? But how many spirals, how many cycles are we going to go through? It says here only 8. But we get 9 acetyl-CoAs. Because that last time when you cleave, you get 2 acetyl-CoAs. So this is a trick that I'm going to test you on. Trick on the exam is that when you find out how many acetyl-CoAs you're going to get, you just take the number of carbons on your fatty acid and divide by 2. But when you find out how many cycles it's going to go through, you have to subtract 1 from that number because you end up with a 4 carbon product. So here you have your 18 carbons. We're going to cut here. So that's the first time. This is the second time. This is the third time, 4th time, 5th time, 6th time, 7th time, 8th time. Because that last time we have these 4 carbons, and when we cut, we get two acetyl-CoAs. Does that make sense to you guys? So you don't have to do a cutting. You don't have to go through the spiral because the last time you get a 2 carbon. So this is why most of our fatty acids are even numbers, because then we go through beta oxidation. We don't have a 3 carbon that we don't know what to do with, right?
You say we're 18 carbons, but it's 7 cycles?
No, 8 cycles.
Or 8 cycles?
8 cycles, because that last cycle, you get 2 acetyl-CoAs. So I need you to know, I give you a number, or say I give you 20. You know that you're going to get 10 acetyl-CoAs, but how many cycles? How many NADHs are you going to get? 9. FADH2s, 9. So you're going to know from that. Okay, let's move on to how much energy we get from, say, that stearic acid. So remember, we have it in our cytosol. We need to get it into the matrix. So this is just like we've done before. So the stearic acid, this is our 18 carbons. Bless you. We're going to take the 18 carbon, and we have to activate it. And remember to put that, to activate it, we go from ATP to AMP. So I'm going to say that it is investing 2 ATPs because it's going from, it's losing 2 phosphates. So in my book, that's an investment of 2. Now, we make 8 cycles. We go through beta oxidation 8 times. So because it's 18 carbons, we get 9 acetyl-CoAs. So we're going to go through that 8 times. So each cycle we get 8 NADHs and 8 FADH2s. Then we have 9 acetyl-CoAs. Let's put that through the citric acid cycle. So this is through the citric acid cycle. Each time we go through the citric acid cycle, we get 3 NADHs and 1 FADH2 and 1 GTP. Do you want me to say that again? So here, let me back up. This is our beta oxidation. We knew from each cycle of the beta oxidation, we got 1 NADH and 1 FADH2. Since we went through it 8 times to get the 9 acetyl-CoAs, we get 1 of each. So that's 8 total. We got 9 acetyl-CoAs from the 18 steryl-CoAs going through beta oxidation. Let's put those 9 through the citric acid cycle. So here, we should say citric acid cycle in your notes. And each time you go through the citric acid cycle, you're going to get 3 NADHs and 1 FADH2. You're also going to get a GTP. So let's take 9 times the numbers I just said. 9 times 3 is 27. 9 times 1 is 9. And 9 times 1 GTP is 9. Remember I said GTP can just transfer its phosphate to ATP. So we're going to count that as an ATP. Now, yes?
Quick question, but why would you not multiply it by 8 if you're going through the 8 cycle?
Remember when, if you're 18 carbons long, you're going to get 9 acetyl-CoAs.
Right.
So this is the 9 acetyl-CoAs that are going to enter the citric acid cycle. So that's why we're multiplying it by 9, because we're going through the citric acid cycle with each acetyl-CoA.
Oh, okay.
We're only multiplying this by 8. We're only going through beta oxidation 8 times.
Okay.
But we're going through the citric acid cycle
To use
9.
up all these.
Use up all the acetyl-CoAs. Thank you for asking that. Now what we're going to do is turn these in. For every NADH, we're going to get 2.5 ATPs. So 8 from the beta oxidation gives me 20. 2.5 times 8 is 20. The 27 is going to also give me 2.5. So 27 times 2.5 is 67.5. FAD doesn't give us as much. It's only 1.5, so let's turn in this 8. We get the 12, the 9, we get 13. So we net for our 18 carbon fatty acid, we net 120 ATPs. That's a lot. All right, now we compared it. How many did we get from a glucose?
30 to 34.
30 to 32. 30 to 32, depending on the shuttle. So but that's not really a fair comparison, is it? Because how many carbons is glucose? 6. And this one is 18. So what we're going to do is multiply. Let's use 3 glucoses so that the number of carbons are the same. So, and let's use, the higher number so we have a fair comparison. So 3 times 32 is 96 ATPs. So we get more energy out of our fats than we do for our glucose.